Welcome to Khetz Tutorials, and in this video I'll be doing the converse of theorem 1. So theorem 1, converse. So this is the converse of the theorem which I discussed in the previous video, and if you haven't looked at that, please go back there just so you understand what's going on here. So this is the triangle theorem, or this is a theorem which actually applies to triangles, where you have a line which is parallel to one side of the triangle and it divides the other two sides proportionally. So now the converse of that theorem says if a line divides two sides of a triangle, so two sides of a triangle, you can just do that to indicate a triangle. So if a line divides two sides of a triangle proportionally, then the line is parallel to the third side. And a diagram is going to be quite useful for this. So you can use a diagram to actually show this. So let's do that. You're going to have a triangle. I'm going to try as much as I can to draw a neat triangle. It's quite hard. Okay, so that is okay. So now let me use another color to have another line cross that triangle over there. Let's say somewhere there. If I could just draw a straight line, that should be fine. Let's just leave it like that. Okay, so the converse of the theorem says if a line divides two sides of a triangle proportionally, then the line is parallel to the third side. So if we're given values for each of the sides which are on this triangle, so if we're given values and we see that BD, let's say BD divided by DA, for example, is equals to CE divided by EA, then we can conclude that the red line divides the two sides proportionally. We can conclude that, but we haven't proved the theorem, or haven't really explained the theorem. This is one part of the theorem. We have actually, let's say we're given values, as I said, and from the values which are given, if we see that BD divided by DA is equal to CE divided by EA, you can also use any other ratio or whatever you want to use. But basically, if you see that the lines on the two sides which are linked by the red line are proportional, then you can make this conclusion, and that is what the theorem is saying. The converse of the theorem is saying. You can conclude that DE, which is the red line, is parallel to BC. So basically, you're going to be given the values. Let's say this is 2, let's say this is 3, let's say this is 4, and let's say this is 6. So BD divided by DA, so let's say BD divided by DA, which would be 3 over 2, which is 1.5, something like that. But we're not interested in the actual value, just the ratio or the proportion. So we can just, you can basically use the final value, it doesn't really matter, which is 1.5. Let's look at CE divided by EA. It is, in our case, it's 6 divided by 4, and that amounts to the same value or the same ratio of 1.5. which means this stands in our case, and we have BD divided by DA equals to CE divided by EA. You could use any other proportion if you like. You can use something like DA divided by AB, and you can also use, okay, so let's start at the top just so this makes sense. You can have something like AD divided by AB, and you can also have AE divided by AC. So let's check that again. That would be AD is 2 and AB is 5 if you add 2 and 3. So that's going to be 2 over 5. And on this side, you're going to have AE, which is 4, and you're going to have AC as 6. So you're going to divide the top and the bottom by 2. Let's check that. So it's 6 plus 4 actually, and 6 plus 4 is 10. So you're going to divide the top and the bottom by 2, and the result will be 2 over 5, which is the same as that. So it doesn't really matter what you use. You don't have to use BD over DA. You can use any of the proportions, but the base thing, or the main thing, is that if BD, or if there is proportion, if there is proportion present, and we are not told that this line is actually parallel, so we are not told that DE is parallel to BC, we can conclude that DE is actually parallel to BC from this relationship, or from the proportion which we have concluded. And that is all with regards to the converse of Theorem 1. That was just me explaining the converse of Theorem 1 and how to actually prove it. Just find proportion, or just prove that there is proportion present. And from that, you can basically conclude that DE is indeed parallel with BC. As the theorem says, if a line divides two sides of a triangle proportionally, then the line is parallel to the third side. And that is basically it. If anything isn't clear, please comment. And if you like this video, just go ahead and give it a thumbs up. If you haven't subscribed, please subscribe. And I will see you guys in the next video.